Hello everyone, my name is Philip. I'm DC number 9 of the GECKO project, and today I'm going to talk about isogeometric acoustic BEM simulation with reduced order models. First of all, a short overview. So as you know, noise is everywhere, and with increasing regulations regarding noise, the numerical simulation of acoustic wave propagation plays a very important role. In this work, I'm using the boundary element method in order to simulate acoustic wave problems. The reason why I use the boundary element method is that you only need to mesh the boundary, and CAD geometry is usually represented as a boundary representation, meaning that they fit very well with BEM. Furthermore, the BEM also inherently satisfies the Sommerfeld radiation condition, which makes it quite attractive for radiation problems. Next on, as numerical methods, as there's no free lunch in numerical methods, the main challenge for IGA-BEM or boundary element method in general is that the system matrix is non-affine, meaning that it is frequency dependent. And even though we use spline-based basis functions and the mesh requirement is relaxed, acoustic wave problems require an increasing number of wavelengths to be resolved as frequency arises. As a result, the number of degrees of freedoms also grows at higher frequencies. Furthermore, spline-based basis functions, such as NURBS, they possess multiple not-span support, meaning that also the cost per degree of freedom is more expensive compared to traditional basis functions like Lagrange. And by performing basically a frequency sweep analysis, that means that we have to assemble and solve many large dense linear systems. A possible solution to circumvent that is to use model order reduction. So for instance, for a given frequency band psi, for omega 1, we have to assemble the system matrix and solve it, and then we move to the next frequency step, omega 2, and as the IGA-BEM system is non-affine and it's dense, that means here we have to assemble it again from scratch and solve it again. And this goes on until we reach omega max. As model order reduction is not a new concept, there already exist some methods for traditional boundary element methods, such as PhD and RBM and Krylov subspace-based methods. Well, the reason for PhD and RBM is that the bottleneck here is that it is very hard to find a cheap error estimator. Furthermore, storage becomes a problem. And especially for IGA-BEM, since we use spline-based basis functions, and they have multiple support on the not spans, the system matrix is often poorly conditioned, and as the efficiency of Krylov-based model order reduction methods are dependent on the spectral properties of the system matrix, this will only lead to moderate reduction. So in this work, I propose a efficient strategy for model order reduction of acoustic IGA-BEM system. This method follows basically a two-step reduction, where in the first step I construct an initial reduction basis using adaptive Krylov subspace recycling, and I use Chebyshev polynomials in order to decouple the system matrix or the frequency of the system matrix. After that, I introduce a second reduction step using reduced basis method in order to compress the size of the reduced order model further. So moving on to the construction of the initial reduction basis. So in this, like I mentioned, I use adaptive Krylov subspace recycling algorithm, which follows here by a bisection sampling strategy, meaning that for a given frequency band psi, I first off assemble and solve partially the full order system matrix at omega min and omega max, and I create my reduction bases and enrich them with the Krylov vectors and check at the midpoint, so here at omega m, if my reduction basis is accurate enough. Hereby I'm using the residual to do that. So here I check basically if the residual is below my set threshold. If this is not enough, I then bisect it again and enrich it now with the Krylov vectors of my omega a, of my new omega a, and repeat this until it fulfills my threshold. With that, I don't have to solve all the systems in the whole frequency band, and I keep basically the number of system assemblies and solutions to a minimum. Furthermore, this is a very fast construction of an initial reduction basis based on the non-affine IGA-BEM system. Regarding the frequency approximation, I use Chebyshev polynomial approximation in order to decouple basically the frequency of the BEM system, where here Ci are the Chebyshev polynomials of the first kind, which are frequency dependent, and Ti and Qi are my coefficient matrices or vectors respectively, and are frequency independent. For the construction of the frequency of the coefficient matrices Ti and Qi, I need to evaluate the full order system matrices at the Chebyshev nodes. Since by using Chebyshev polynomial approximation, we don't need the derivatives of the system matrix. It is non-intrusive, and another highlight of Chebyshev polynomial approximation is that we get a uniform error distribution in C. So with that, we basically have with the initial reduction basis and the Chebyshev polynomial approximation, we have a reduced affine IGA-BEM system, and by taking advantage of this new reduced affine system, we employ our second step, which is the reduced basis method. So for the reduced basis method, we basically have our solution of our reduced affine system, and we enrich basically our second reduction basis by using a greedy method. So picking out the frequency points where we have the highest residual. And this basically enables, and this is done until our second threshold is basically fulfilled. So we enrich it until our second threshold is fulfilled. Now to the results. So in my first result, or my first example, I'm using a sphere which has 6 non-conforming patches, and we are using polynomial degree of 4. For the Chebyshev polynomial approximation, we go up to degree m equals 25, and our frequency range is 1 to 1000 Hertz with a step size of 1 Hertz. For this sphere, we have 351 degrees of freedom, and our tolerances are 1% for the initial reduction basis and 0.1% for the RPM. So with our proposed two-step reduction method, we can reduce basically the degrees of freedom to 17 from 351 degrees of freedom, and we only need 3 full system assemblies for the construction of the reduction basis. And it usually, as we can see in the plot, the residual plot, the residuals are below the residual tolerance, except for at 3 specific frequencies, which are basically the resonance frequencies. So at these points, since it is not sampled, it exceeds the residual limit. But as we here compare the full order model with the reduced order model, there's actually no visible difference between form and ROM. With the reduced order model, we can speed up especially the system assembly by a factor of 10 to the power of 2, and also the solution by 36. For the construction of the initial reduction basis, so the offline costs, for this example, the proposed method needs 14 minutes, and for the Chebyshev polynomial, or for the construction basically of the coefficient matrices, 15 minutes. As a second example, or more industrial examples, I have the car hood, which has 14 patches, and we model it with polynomial degree of p equals 2, and have a frequency range from 1 to 500 Hertz with a step size of 1 Hertz. The degrees of freedom here are 1053 DOFs. With the proposed two-step reduction method, you can reduce the degrees of freedom to 12. And for this case, the residual is below our threshold. For the construction of the initial reduction base, we need 7 full system assemblies. And as you can see, the reduced order model follows hereby also, or is nearly identical to the full order model. Regarding the speed up factors, with the reduced order model, you can speed up basically the system assembly in the online phase by a factor of 10 to the power of 3, and the solution by 10 to the power of 2. For the construction of the initial reduction basis, for this example, the proposed method needs 36 minutes, and for the construction of the coefficient matrices, 2 hours and 20 minutes. And the construction of the second reduction basis is negligible, as we take advantage of the affine reduced representation of our IGA BEM system. So with that, I think we have shown an efficient model reduction scheme for acoustic IGA BEM systems in order to accelerate the frequency sweep analysis. And as our results show, we could retain its key properties. And that's it. Thank you for watching.